Okay. Buongiorno, come stai? Tutto bene? Sì. I'm here to talk to you about optimizing resources in Kubernetes, and I'll give you some ideas of what we are doing at my team and how to optimize at different levels if you're running on Kubernetes. So hopefully you get some ideas for that you can put in practice like Monday. Eager? Okay. So before we start, like, who is using Kubernetes today? Who is using Kubernetes in production? Okay. I'm not going to ask who knows what Kubernetes is. Okay. Just in case. Um, I'm a principal scientist at the Adobe Experience Manager cloud service, and I've done a lot of open source work. That's my background. I've done the Jenkins Kubernetes plugin, and I've contributed to a bunch of open source projects, and that's where I come from. I'm also part of the Google Developer Experts because I talk a lot about Kubernetes and these sort of things that are now everybody's using now. And before we start into the meat, just explain a bit what Adobe Experience Manager is so you understand our use case better and what works for us and what doesn't work for us. So maybe it works for you or it doesn't, depending on your use case also. It's a content management system. It uses Java. It was an existing Java OSD application that has been around for a long time. And people were running it on-premise or on the cloud. But now, some years ago, when I joined Adobe, we launched the cloud service. So we are running this for our customers, and we're running this at a decent scale. It uses a bunch of open source components from the Apache Software Foundation, like Sling, OSGI, libraries. An interesting case is that it has a huge market for extension developers. People write code that we run on AEM for them. So that's a bit special. We're running on Azure, the cloud service. We have more than 50 clusters right now. And because it's a content management system, people want to run as close as their users as possible. So we have any region that we can get a hold on. Typically, we just run it there. We have a region in Switzerland, and for some reason, some companies want to run in Switzerland and keep their data in Switzerland, not leaving the country. We have multiple teams building services, and different teams have different requirements. So we don't enforce languages or anything like that. Trying to do you build it, you run it, and we use APIs to talk between services or the Kubernetes operator patterns. We use namespaces. If you know Kubernetes, we do isolation on namespaces. Namespaces do not isolate everything, but they isolate the networking, quotas, permissions, things like that. So that's one way of doing it. What we call an AEM environment is a set of services that provide this application to the customer. So customers can have multiple environments, and they can self-serve their environment. So they can go and click and say, oh, I want a new environment. This triggers a set of events, and basically this translates to multiple Kubernetes namespaces. Imagine if you have dev stage production environments, they would get 3 different namespaces. And I like to call each environment a micro monolith. Right? We give every customer, their own set of services. We have also shared services, but for AEM itself application, we give them an application for themselves that is not shared. This is a very cool pattern of Kubernetes where it's very easy to take something that is running on-prem or somewhere else and just take it to Kubernetes, and then you can start building other services on top of that. Our scale is, this is probably a bit old, a month or 2 old. We have 70,000 of these environments, AEM environments. This translates to over 200,000 deployment objects in Kubernetes, and more than 10,000 namespaces across all these 50 clusters. We use extensively init containers and sidecar containers to do division of concerns. So this is another pattern from Kubernetes that is kind of very easy to follow when you are migrating into Kubernetes. So you have your application is one container. You want to add things that may be like logging or security or something. You don't need to keep adding things to your application. You can use init containers, sidecar containers that run either before your application or at the same time as your application, and you have different services, kind of, without being separate services talking over the network, but living together in this the pod concept of Kubernetes. So, on the scaling and resource optimization. As I mentioned, each environment is this micro monolith, and we are looking for ways on the, let's say, lower level teams that we are managing more infrastructural things. We're looking for ways for all these teams to benefit from scaling improvements or resource utilization improvements. So we are not going into each. So things that can help is obviously optimizing your application, but we're looking also for ways that apply to any application running on Kubernetes or any service running on Kubernetes. Who is familiar here with resource and limits in Kubernetes? Not that many people. Okay. So Kubernetes workloads have these two things, requests and limits. Simplifying it is request is how many resources are guaranteed, limits is how many resources can be consumed. And they are not the same. And these requests and limits can be applied to CPU, memory, and ephemeral storage. What happens when you go over the limit on CPU? Your container is going to get throttled. The process inside the container are going to get throttled. What happens when you go over the limit with the memory? The kubelet is going to kill your process. It's going to restart your container. What happens when you go over the limit on the ephemeral storage? Your pod is going to get evicted. This means your pod is going to be removed from that node, and Kubernetes is going to do what it always does. Okay, I need another pod, and it's going to start it somewhere else. So those are the main things that you can find when you go over limits. So going into the CPU part. What are CPU requests used for? A lot of people don't really get this because it's not easy to get. It takes a while to grasp how Kubernetes deals with CPU requests. CPU requests, as also memory requests, are used for scheduling. So you say, I need one CPU for my pod. Kubernetes is going to look at all your nodes and say, OK, this node has one CPU available on the request number that they manage, and then it's going to put your pod in there. But after that, after the pod is running in that, or the container is running on that node, this is used as a relative weight with the other containers running in the same node. It's not the number of CPUs that can be used. Okay? So one CPU request means it can consume one CPU cycle per CPU period. So if you have two containers that only request 0.1 CPUs running on a node with 32 CPUs, and they are using as much CPU as they can, both can use 16 CPUs each. So you are not limiting them. It's a weight between the two. The two have the same weight. Both of them can run at the same time, consuming all the CPUs they can at up to the 50% between the two. Limits in Kubernetes is different. And this, everything in Kubernetes translates to C groups and the kernel C groups. And limits translates to quota and period. So when you say, I don't want this process or this container to use more than one CPU, it's not really that it's limited to use one CPU all the time. This uses the kernel period, the cgroups period. The period by default is 100 milliseconds. And the CPU limit you set in Kubernetes means the number of CPU cycles that can be used in that period. And after you run of those cycles, your container is throttled. So I'm going to show you some examples to try to understand this better. If you set 500 M, so half CPU more or less, this means that every 100 milliseconds, your process, your container can use 50 milliseconds. If you say 1 CPU or 1,000 milli CPUs, it means that every 100 milliseconds you can use the CPU for 100 milliseconds. This is challenging for Java applications or things that use multiple threads. Because, for instance, if your limit is 1,000 or 1 CPU, and you have 4 threads, this means in 25, and all of them are using CPU, this means in 25 milliseconds, you may already use all the CPU you had available in that 100 millisecond period. So how does this translate? Is if you are serving web pages, that means you're going to have long, very high latency, because this can only process, or you are going to see high variation, because if your container is busy, it's going to be throttling. It's not going to do anything for 75 seconds, 75 milliseconds every 100 milliseconds. So 3/4 of the time it's not going to be able to do anything. So I was trying to show here an example. Let's say you have a machine with 4 cores, and you have a limit of 1 CPU. That's fine. If you have 1 thread, that's fine. The thread runs for 100 milliseconds, then a new period comes in, another 100 milliseconds, so you can use 100 milliseconds of CPU every period, so all is straight. But if you have 4 threads, and they're wherever they're running, that means in 25 milliseconds, you are done. Then throttling for 75 milliseconds. So this is something that is critical if you have more of real time, or you're doing something that your customers can see, or something like that. And that's interesting, especially for Java or any multi-threaded application, because people tend to play with the limits, and then you don't realize this. How do we scale our application, or how can you do it on Kubernetes? There's multiple autoscalers. One of them, the most typical one, is the cluster autoscaler, unless you are running on-prem, which is every time I need more resources, I increase the cluster. I add more nodes. And when I don't need them, I shut them down. So the cluster autoscaler can be based on CPU and memory. What we run is we have some headroom for the spikes. You can configure Kubernetes to have a little bit of the cluster autoscaler to have a little bit of headroom, because if you need something, depends on your workloads, right? But if you need more CPU or more memory or something, you don't want to wait for the cloud provider to give you a new node. So you want to have always a little bit of headroom. We have multiple scale sets, virtual machine scale sets, or what is called VM groups, in different availability zones, because if an availability zone goes down, you want to keep running with the other two. And at the scale, it's easy to cause denial of service by yourself, because we have issues now. This better it was years ago, where the cluster autoscaler is hitting the cloud provider APIs, and you may get throttled if you're hitting them too often. And then it was like, oh, the cluster is not scaling. Oh, okay, because we consume the rate limiting of the cloud provider. I think that should no longer be the case. We have a maximum number of nodes for the cluster autoscaler, because we don't want, if we make a mistake, we don't want to start creating nodes with no reason. We use the least waste scaling strategy, which is trying to optimize. You have different strategies in Kubernetes. This one is trying to optimize after you scale up, having as less CPU unused as possible. And obviously, if you run with the cluster autoscaler, you're going to have big savings because your cluster is going to be shrinking and growing all the time. And for us, it could be 30 to 50%. That if you were with a static cluster always maxed up to the maximum capacity you need. A typical day would be something like this. This cluster was running between 50 and 100 nodes or 100 something. And maybe people are using it during the day in whatever region it was, and it's scaling up and down all the time. This is what it looks when you make a mistake somewhere, and this scales up to the max number of nodes. You fix the bug, and then it goes back to normal, right? So if you don't want to pay a huge bill, that's important to limit it and watch if you are going there. The other autoscaler you have in Kubernetes is the vertical pod autoscaler, which increases or decreases the resources of each pod. It's called the VPA. And for each deployment, you can say, oh, OK, if based on some metrics, you can say, give this pod more CPU, or this container in this pod more CPU or more memory. The problem with VPA until 127, Kubernetes 127, is that it requires restart of pods. So that's now it's in place. VPA is available in 127. It makes it slow to respond because if you say, oh, I need more memory, OK, now I'm going to start another pod with more memory, kill the old pod, and then everything has to move around. So the time it takes for the new pod to catch up and all these things, it makes it slow to respond. And it has several ways of operation. One of them is auto. And then if you set it to auto, it's going to restart your pod. And probably you don't want to do that. As I said, this was until 127. So you have on next start, is another option where, OK, I see that this pod is using 20% more memory typically. Then the next time I start another pod, Kubernetes is going to give it 20% more memory. So that's more reasonable. We only use it in some developer environments to scale them down when they are not used, and only for some containers, not the critical application. And the problem with Java, I mean, who's here? Who's a Java developer here? OK? Not that many people. Half of the room. JVM, as you know, with the memory, you set the memory heap to a fixed number or a fixed percentage. And Kubernetes or the kernel, they don't see if that memory is actually used or not. So it's hard to say, or if you don't have any other metric, it's hard to say, oh, this needs more memory, this needs less, because Kubernetes doesn't see what is actually used. For us, this doesn't save a lot. Probably now even less than 5%. We're going to be looking into the in-place scaling, but that also has its challenges. Because what if you have a Java application where the heap memory is set, it doesn't matter that Kubernetes gives it more memory. It's never going to use it. And if you take out memory, it's going to crash because that memory is fixed. So you could do it for CPU, for instance, but not for memory. The other autoscaler, also well known, is the horizontal pod autoscaler that is creating more pods when needed. So we do scaling on CPU and requests per minute. And the advice is do not use the same metrics as VPA, because otherwise you're going to be scaling in both directions at the same time, and it's going to be messy. Things are not going to work as you expect. CPU autoscaling is a bit problematic. For instance, for a Java application that requires a lot of CPU during a startup, we've seen where, OK, during a startup, the CPU is through the roof. The autoscaler says, oh, I need more pods. The new pods go through the roof on the startup. And then you have this cascading effect that can cost resource. Instead of reducing resources, you are actually using more than you should. Or if you have periods where the CPU is very high, because somebody is making a mistake on their code or something like that, then you have the same issue. Yeah, periodic tasks. So sometimes a customer is running a periodic task, that's a spike in the CPU, creating a new pod that is also going to run that task is not going to help. And yeah, the spikes in a startup is the cascading effect that I was mentioning. On our case, we are warming up the AEM application on a startup. We are doing some cache warming, and we use RPM autoscaling, which fits better use case. For you can be different. I don't know if you are doing AI training, because everybody's using AI, of course. And if you are doing something else that is more batch oriented, then you have a different case. Maybe you want to use them when there's more nodes around, where there's more empty space around. It can be something like that. And request per minute works for us as long as customers don't have expensive requests, because if you have a request that needs a lot of processing, of course, you have very low number of requests per minute, but they need a lot of CPU, so you have to balance these things. As we are saving 50, 75%, because we run typically between 2 to 8 pods per customer. Some customers we are running up to 60 pods, and obviously this is all going up and down depending. If you have a very high, I don't know, a website, a commerce site or something, you're going to have periods where you need to scale up more. You're going to have periods where you have barely no traffic during the nights, and that sort of stuff. This is the number of pods at the top. So this one is running up to 9 pods, I think. And you see it's all the time going up and down, and it kind of looks like the number of requests per minute that we're getting. So in periods of low traffic, you have less pods. When to use VPA, when to use HPA, depends on your use case. A lot of times it's more effective to give a container more memory and more CPU than running in parallel. Everybody knows that distributed computing is hard. Especially in Java, also, a lot of times it's going to be better to run twice the memory than just 2 pods with the same memory. But a lot of cases, you're also going to need at least 2 pods running for HA. You don't want to run one, it goes down for whatever reason, and then you have an outage. And who's here using already HPA or VPA? Yes, some people, okay. Another one is ARM architecture. Who is using ARM? Other than your MacBook? Okay, just one person. Why are you not using ARM? So, in our experience, ARM, we're saving around 20% just by switching to ARM. And it's cheaper, and it has better performance. Again, it depends on your use case. If you are doing Bitcoin mining or if you're doing AI training, that may not be the case, but you're going to be using GPUs or whatever. And for some things like Java, again, it's very easy, because you just say, instead of using the base image with the JDK in Intel, I'm going to use the JDK on ARM. Done. Everything else works. It's magic. So this is very good. And a problem that we have, for instance, is availability from the cloud provider. So what we do, and we have a small issue this week, and what we do is we build the images multi-architecture. So we make sure that our pods we have an image that is multi-arch. You can do this with Docker or any container runtime. So you build your image, so it has both the ARM and the Intel version. You put it up there, and Kubernetes magically will, if you set the right, it's called pod tolerations. You can say, this pod can run on ARM or Intel. Kubernetes, I'm running, this is an Intel node, I'm going to use the Intel image. This is an ARM node, I'm going to use the ARM image. So you can have a mixed cluster, or with ARM, Intel nodes, and Kubernetes can use either of them. So that's one that we've been using lately. Something that we do, that we build ourselves, is something that we call hibernation. Some environments, development environments, well, we call them sandboxes, we can scale them to 0 when they're not used. So we use a metric that says when was this environment last accessed. If it's under 4 hours, if it's over 4 hours, we just scale down to 0. We delete a bunch of other objects. We save them, but we delete them from the cluster because the clusters can also be limited not just on CPU memory, but how much stuff you have stored on the Kubernetes control plane, like etcd. And right now, our limit is how much stuff we are storing on etcd. And we delete a bunch of things from Kubernetes, scale it to 0. We did a very simple one. You can use, we do a Kubernetes job. We implemented this 2-3 years ago. We scale down if there's no activity, and the customer gets a message that, oh, you want to dehibernate, just click here. Ideally, you would dehibernate it automatically when you get new requests. You can do this more as a function as a service. You can use Knative. There's some tools out there if you want to go into the complex route. On our case, for the JVM, it takes 5 minutes to start, so it's not ideal to do. We cannot do function as a service because that. But this saves us 60-80%. We have our rate of sandboxes hibernated is around 85%. So if we were running them, we would need way more capacity. Today, this was implemented some time ago, but today you have KEDA. It's a Kubernetes event-driven autoscaler, and you can scale any deployment in Kubernetes based on events. And if I were to re-implement this today, I would use KEDA. Actually, we're looking at KEDA to re-implement it. KEDA can scale based on messages on Kafka, cron schedule, events from your cloud provider, Google Cloud, Kubernetes workloads. So if you say, oh, if this other deployment scales to 0 or to whatever number, scale this other one too. So it's very powerful to be able to just declare what you want based on other metrics. The Kafka one is the typical, okay, if I'm getting many messages through here, scale it up. So you are not limited to the scalers that come by default with Kubernetes. So that's a cool project, open source. One thing we started looking at was how do we optimize other resource, which is CO2 emissions, right? Obviously, the less we use, the cheaper it is, and the less CO2 we emit, right? So there's also the cost benefit. But for CO2 emissions, if you look at if anybody has been this emissions map, you can go to, what was the name? I'll have it later. It's, I forgot. Electricity maps, yes. You can see live how much each country or region is, how much CO2, how clean the energy is. So you could say, oh, if I run in the Sweden region, most likely it's going to be cleaner than if I run in Germany. So if you can do that, this is one way. We are kind of limited with what our customers want, where our customers want to run. We cannot tell them, you want to run in Switzerland, but no, we're going to run your own France. We cannot do that. But this is one thing that you could do if you don't care about regions. And you can go to the maps and you see like Washington, there's a data center in Oregon. There's data centers in Washington, which are better than the data centers on the East Coast. And you could do things like that. Region is one, but the other one you can see here per hour. So what we're thinking about doing is cron job optimization. So, and the URL is that. So why are we all doing cron jobs at 1 a.m. in the morning when the cleanest energy is at noon, right? So this is one thing we're looking at. We're not going to save any money, but we're going to have less emissions. Other scalability concerns that you may have, and we have. The etcd limits that I mentioned before. Kubernetes is not a database, although we all try to use it as such. And we have, as the more objects you store in Kubernetes, you're going to run out of the etcd limit, which is by default, I think it's 8 gigs, depending on the cloud provider and the installation of Kubernetes you have. But at that point of time, etcd goes into read-only mode, and we had this before, and it's not something you want to see in your cluster. You cannot create anything, you cannot delete anything, it's not nice. So the amount of space you have is not infinite. So if you keep creating secrets, config maps, these things, you have huge deployments, you have thousands of them, you are going to fill it. There's also the problem with memory at the control plane. Every mounted object will create a watch. If you mount a secret, you mount a config map, this creates a watch, and the number of watches will cause increased memory usage, and this will increase the response time of your Kubernetes API, and after a period of time, I think it's 1 minute or so, your requests get dropped, so nothing in your cluster is going to work. So if a pod dies, but your API is not responding, Kubernetes is not going to be able to create another pod, your service is down. It's better to create less objects with more data than too many objects because of the watching thingy, the memory usage. And there's one thing in Kubernetes that are immutable secrets of config maps that you can use to avoid watches. So you can tell Kubernetes this secret, this config map is immutable, and then it will not create a watch for it. And of course, do not use etcd as a database. And another one that we recently found out or worked on fixing was the max pods per node. The default in Kubernetes is that 110 pods per node. You may realize, oh, we need bigger VMs. Now you create a VM that is big, but you don't realize that it's not being used. Because Kubernetes, no matter how much memory is there or CPU, is not going to put more than 110 pods there. So if you have big nodes, small pods, you're not. Take a look at these numbers because otherwise you're not going to be using. To wrap up, we talk about a few things about resource optimization. From the application, obviously you can tune the CPU, the memory in Java garbage collection. From the Kubernetes ecosystem, you have cluster autoscaler, HPA, VPA, KEDA today that will help you do the autoscaling. Then you can do this both at application and infrastructure levels, so a combination of both will give you or help you reduce the resources you are using. So I hope that helps you and you can take some ideas with you that are useful. All right? If you have any questions. Ask me one question. Did you do any optimization for networking? Yes, we use Cilium. And we had issues with the load balancers in front of the clusters at some point. We had issues with the ingress controller because we have hundreds of ingress routes. It takes, every time you change one, the Envoy proxies have to be reconfigured, things like that. So that's why we are deleting ingresses when we are hibernating services, because that way the time it takes to reconfigure the ingress is lower.
Yes. Nice presentation, thank you. Maybe just a question related to canary testing, A/B testing. You know, if you want to release new code, how does it affect the resources? Because of course, if you're trying to release a new version and you want to test in production, because we do that.
Of course.
Of course, it's mandatory, and in that sense, I mean, if you set a limit or resource, it will have an impact, right? you have an experience something like that, or do you have an experience on that?
Yeah, actually, another talk that I usually give is Argo rollouts. It's about Argo rollouts. Argo rollouts allows you to do progressive delivery. One of them is Canary deployments. And it's very easy to do Canary deployments with Argo rollouts in Kubernetes. So what we do when we make a change, Argo will manage the old version and the new version. And you can do all sorts of configuration to say, oh, I want the new version to not be available to the external world, just internally for 10 minutes. And then you can do, oh, I want 1%, I want 20%, so you can gradually roll this out, defining yourself what's the rollout schedule that you want. And the most interesting part is that you can set up metrics, like if the number of 500 errors goes over this, consider the rollout unsuccessful, and it goes back automatically to the old version. So we do that. It also has blue-green, but in the case of resource optimization, blue-green, especially if you run it over a long period of time, you need twice the resources. So we are playing with the Canary rollout for this. Yes. Okay. Well, thank you. Grazie. Grazie mille.